Climate change is considered to be one of the greatest challenges of our time.
The last 30 years, global mean surface temperatures have gone up, and a 1 degree rise. The theory is that it's human-induced carbon emissions.
Reducing the air pollution on the planet is a big challenge, and everybody is part of it, and we need to find solutions.
We need a concentration to care about the climate change.
Every increase of 1% of a population will result in about 1.4% of the total energy consumption.
To tackle the climate change issues, need to encourage all the professionals to be involved.
Action needs to be taken now, before it's too late.
China is urbanizing very rapidly.
The cities have to build up a lot of high-rise buildings.
And as the standard of living rises, people become more prosperous, more aware of what's possible.
People moving have higher expectations for their indoor environment, in particular the thermal comfort issues.
And the people freedom to use the air conditioning.
People will start to install air conditioning at a huge rate. And there's a spectacular carbon threat in that.
If we keep using large amounts of energy via the air conditioning, it will release a lot of anthropogenic heat flux, and these will further result in global warming. So this is a vicious cycle.
It's not this Aries problem, not the Chinese problem, and it's global, because we are only one world.
In 2015, China had signed the Paris Accord, and to celebrate that, George Osborne provided money for research into how to deliver this low-carbon future. We won one of the 3 big projects with all of our colleagues and friends in China, and it is co-funded by the National Natural Science Foundation in China as well. So it's a wonderful collaborative project between China and the UK. The local project is low-carbon, climate-responsive heating and cooling of cities. Is about how to make people comfortable, particularly in hot summers.
In the hot summer and cold winter region of China, there are about 40% of population living here.
Which is continent size, 550 million people, 9 billion square meters of buildings. If China starts building buildings to the sort of Western, North American standards that we've become used to at the moment in this region alone, 90 to 135 billion kilowatt hours of electricity are used every year. And we think that could go up easily to 550 billion if good practice air conditioning is installed.
The building department have at least 1/3 of the responsibilities for reduce the CO2 emission of the whole society. If we want to reduce energy consumption and the CO2 emission of the buildings, the priority should not be the new buildings.
Chinese construction tends to be concrete framed. Every time it's demolished, thrown away, there's a massive carbon bill. 10% of the carbon emissions due to mankind come from making cement. So we want to keep those frames and reuse them. The task is to adapt the buildings in an affordable, quick and practical way, but use not just no more energy, but less energy than they do at the moment, much lower carbon emissions.
In order to address the problem effectively, the research team chose 2 cities with extreme climates as the basis of their case study.
Chongqing and Hangzhou are 2 furnace cities. Chongqing is the hottest city, and Hangzhou is like the 3rd hottest city in China right now. If our building retrofit scenarios can help adaptation in a worse scenario, it definitely can help people to survive and adapt in a less worse scenario.
Our method is to look at the cities, survey them, and then to distill in a rigorous way the absolutely most typical types of buildings, collect real data over 2 years.
Our Chinese colleagues installed both indoor and outdoor sensors for these case study buildings.
We give all these results and data to the University of Cambridge, and they use it to predict the future scenarios of the weather and the indoor environments.
To gain a better understanding of both the current and the retrofitted building's predicted thermal performances, the team used Fluidity, a computational fluid dynamics modeling tool that simulates both inside and outside airflows within complex, dense urban environments. To complement this data for simulations of indoor thermal conditions and energy consumption of both existing and retrofitted scenarios, digital analytical tools were used for building energy and climatic modeling. Such comprehensive analysis will provide the basis for decisions leading to future retrofitted adaptation designs.
We don't have a universal wind pattern around the buildings. Each wind pattern is driven by the surrounding buildings, but also the shape of the building we are looking at. I can add or remove any building. I can change the landscape of the area. I can see how this will influence the local wind pattern and the local temperature at the scale of a flat, basically.
These are very complex models. Now we're probably the first people to be able to look at the air blowing through a city and around the buildings and then into the buildings and out through the other end of them and see all of this happening simultaneously. And then out of all of that, do this all-important diagnostic, try and work out what could we do to make them perform better, be much more pleasant places for the people living inside them, start to develop the detailed design of what you might do to the buildings, cost them all out, and present them as completely viable, realistic possibilities. Simple sun shading will deal with an awful lot of the problem. You don't want to keep out the high-level winter daylight, and you also want to be able to see the view, so our sunshades project out of the facade 45 degrees and lift themselves up as sort of kite shapes. We have the pressures taken all the way around the facade at a particular floor level, and the pressure coefficients, they are so similar that they won't promote an airflow. So just opening the windows doesn't help at all.
We need to think about doing some building retrofit to help increase the natural ventilation potential for this area.
For a human being to be comfortable in an internal environment, they need about 10 litres per second of fresh air. But to keep them cool in hot weather, you need much more air being forced through the space. That's usually done with fans and air conditioning systems. But actually you can do this quite naturally and passively with no energy at all.
For the Liubo building, the tower building, we have wind catcher and we have chimney to remove the hot and polluted air that are in the flat.
If you put ventilation stacks on the outside of the building, that you can generate huge airflows.
The team simulations showed that by retrofitting sun shading, temperatures could be reduced by at least 2 degrees Celsius. Wind catchers and stack ventilation with high ventilation flow rates achieved a drop of around 4 degrees Celsius in temperature, accomplishing the expected thermal comfort standards for this area of China.
The Liubo Tower alone would save 380,000 kilograms of carbon dioxide a year. It did our adaptation scheme.
We are talking about retrofitting millions of buildings, which could help the city reduce 40% of energy consumption.
So this project will have greatest impact. This will improve energy efficiency and will help the Chinese carbon reduction target.
The team has therefore found a sustainable, groundbreaking design solution, one that can be retrofitted easily at a low cost and adapted to other regions around the globe. This new vocabulary, a cutting-edge set of adaptation components, can not only help achieve thermal comfort standards, but also dramatically reduce energy consumption and global carbon emissions.